In this lecture, we want to talk about evaluating limits algebraically, and there's sort of two halves to what we want to discuss today. The first half is what are the functions that we can find the limit just by plugging in the number, and then we also want to look at the functions where we might need a little algebraic manipulation before we can plug in the number, because you can't just plug in the number if it's not in the domain. For example, 1 over x minus 1, you can't plug a 1 in for x because you would get 0 on the denominator. Anyway, so again, to evaluate limits algebraically, let's remember that we have evaluated limits using the graphical method, so just by looking at a graph. And we've also evaluated limits by using the numerical method, so by looking at tables and successive values of x, and then what are the successive outputs, what do they get close to. And we've seen some examples where those two methods are not the most precise methods in the world, and so we'd like to have a way to not have to rely on these two methods. So how do we compute limits algebraically? So we'll look at some theorems, and we need a starting point. So let's start with the parent functions. Remember what the parent functions are. That's just the power function, the sine function, and the exponential. So these functions all have the property that the limit as x approaches c of any one of these three functions is just f of c. In other words, you can just plug in the number as long as c is in the domain of the function f. So the domain of these two things is all real numbers. So for these two functions, you can take c to be anything you want. Remember, the power functions, though, depending on what r is, the domain can change, so you just need to be careful. For example, if r is 1/2, then the domain of x to the 1/2, or square root of x, is just all real numbers bigger than or equal to 0. So this theorem would only work for the function x to the 1/2 as long as c is a number bigger than or equal to 0. Okay, the way we will verify this theorem is just to maybe draw a picture. So we'll still have to depend on the graphical method for these things, but then once we start to look at other elementary functions, we want to use our operations and another theorem. So anyway, you can just see by drawing a graph of sine of x, for example, what the limit will be. So if I've got the function y equals sine of x. Right, so here's the function sine of x, and here's pi over 2, and let's say right here is pi over 4. So as x gets closer and closer to pi over 4, the y value gets closer and closer to the sine of pi over 4. Right, that's a solid dot. So in this case, limit and value are the same thing. We can see that just by looking at the picture. So when you plug in pi over 4 to sine of x, you get 1 over square root 2. So the limit here is just sine of pi over 4, or 1 over square root 2. To actually prove that the limit as x approaches pi over 4 of sine of x is 1 over square root 2, that's a rigorous process. Right now, we just want to use the graphical method and our intuition. And then for the rest of the elementary functions, we'll want to be a little more precise. Right, here is a very important theorem that will allow us to evaluate limits algebraically. So now we don't have to use tables and we don't have to use graphs. So here's what the theorem says. Suppose that the limit as x approaches c of f is equal to L, and the limit as x approaches c of g of x is equal to k. In other words, suppose that both of these limits do exist. If one of these limits fails to exist, this theorem has no meaning. You cannot apply any of these limit laws, if one of these limits fails to exist. And you'll see an example of that later, I'm sure. So the sum law for limits says the limit of the sum is the same thing as the sum of the limits. In other words, the limit symbol goes through sums and differences. All right, so the limit of the sum is just the sum of the limits L plus K. Limits behave well with respect to constant multiples. In other words, the limit of the constant multiple is the same thing as the constant multiple times the limit. So the limit as x approaches c of cursive k f is just cursive k times L. Limits go through products. In other words, the limit of the product is the same thing as the product of the limits. Limits go through quotients. So the limit of the quotient is the same thing as the quotient of the limits, as long as that bottom limit is not equal to 0. As long as k is not equal to 0, you can apply the quotient law. So again, before you can apply any of these laws, it is critical that you check that the two limits that you are working with, both of those must exist before you apply one of these things. And here's an example using the limit laws and that previous theorem, or the first theorem we looked at, in order to evaluate this particular limit algebraically. So we want to evaluate the limit as x approaches 2 of x squared minus 3 over 4x plus 1. So how are we going to get a final answer? Well, first thing we need to observe is that this thing is a quotient. So we should use the quotient rule for limits, the quotient law for limits. So we know that limits go through quotients. In other words, the limit of the quotient is the same thing as the quotient of the limits, as long as this denominator is not equal to 0. I think we'll be okay. If we get to some point and we find that this thing is 0, we'll need to try some other method, but we'll be okay in this example. So the limit of the quotient is the same thing as the quotient of the limits. That's limit law 4. That's how I got from here to here. Now, how do I get from here to here? So I've got the limit of a sum. Differences are the same thing as sums, right? It's add the negative anyway. So I've got a limit of a sum, a limit of a sum. We know that the limit of a sum is the same thing as the sum of the limits. So from here to here, the limit of x squared minus 3 is the same thing as the limit of x squared minus the limit of 3. And then in the denominator, I've got the limit of 4x plus the limit of 1. So limits go through both of these sums. Now, how do I get from here to here? So here I'm going to use the product law for limits. So the limit of x squared, remember x squared is just x times x. That's a product. So the limit of x times x is the same thing as the limit of x times the limit of x. That's just the limit of x squared. So that's the product law for limits. So that's how I got from here to here. And now, how do I get from here to here? Well, I've got a constant multiple. So 4 times x. So I'm going to take that 4 and write it on the outside. That was limit law number 2. And so now finally, how do I get from here to here? Well, that's just that theorem that says if you've got power functions, and you can think of constants as power functions, then you know you can just plug in the number. So when I plug in the number 2 for x, I get 2 squared. When I plug in the number 2 into the constant function 3, I just get 3. And then when I plug in 2 in for the power function x to the 1, I just get a 2. And then the limit as x approaches 1 of a constant 1 is just 1. So that's how I got from here to here, just using that theorem that says we're allowed to plug in the number for the 3 parent functions. So now I've got 2 squared minus 3 over 4 times 2 plus 1. That's 1/9. If you observe, if I let this thing be f of x, then this is the same thing as just plugging the number 2 into this function f. So for example, this is the same thing as f of 2, which is nice. So not only can we plug the number into the 3 basic parent functions, we can also plug the number into a lot of other examples using those 4 limit laws.